As we move on to chapter 6, we're going to be starting to focus on the normal distribution. And first we want to talk just in general about the shape of a normal distribution. The normal distribution is a perfectly symmetric, mound-shaped distribution. And we looked at this earlier in the year. We talked about it being the bell curve. It's commonly referred to as a bell curve or a normal curve. And our notation, I don't know, this is a little bit blurry, but our notation is right here. And the notation says that x is a part of the normal distribution, but instead of having the endpoints like we do in a uniform distribution, we're going to list the mean of the distribution and the standard deviation of the distribution inside of our parentheses. Because unlike the uniform distribution, these distributions go on forever to the left and to the right. So that is our general shape, and that's the notation we use to help us represent a normal distribution. The center of a normal distribution is located at the highest point, so the very peak of that mound of the distribution, and the measures of central tendency are equal. So the mean, the median, and the mode are all the same. You think about the mean, if you averaged all of these values, your mean would be right here. The mode is the highest one, so that would be the mode, and then the median, remember it divides it into two equal parts. So in our case, we've got 50% to the left and 50% to the right of that highest point there. So the measures of all three central tendencies are equal. And then note this center peak divides the data into those two equal parts. So 50% above the middle there and 50% below the middle. When we talk about the spread of normal distributions, the most common way that we want to measure the spread of normal distributions is with the standard deviation. Or remember, that means it's the typical distance away from the mean. So measuring the distance from the center, either to the left or to the right. The standard deviation indicates the distance from that maximum peak of the data because of the symmetry of a normal distribution. Here are some examples of different standard deviations. You'll notice if the standard deviation is smaller, the peak is higher because everything is closer to that center line. But as the standard deviation gets smaller and smaller, like in this case with the red one, we've got 7, a standard deviation of 7. Notice because your standard deviation is much wider, the peak is much lower and the data is more spread out left and right. Standard deviation of 4 is kind of in between those two. So now that we've gotten the introductory stuff kind of out of the way, we want to focus in on section 6.1, the standard normal distribution. So first, again, just to remind us, a continuous random variable is normally distributed or has a normal probability distribution if its relative frequency histogram of the random variable has the shape of a normal curve, which means it's bell-shaped and it's symmetric. Suppose that a random variable x is normally distributed with a mean of mu and a standard deviation of sigma. Then the random variable z, we're going to define that as x minus mu divided by sigma, is normally distributed, and the mean becomes 0. The mean will equal 0, and the standard deviation will equal 1. If you remember, we actually talked about these z-scores earlier in the year. We had two different formulas for them. One was for a population, and that was x minus mu over sigma. The other one was for a sample, that was x minus x bar over s. But either way, we were doing the same thing, and that's where this capital Z, this random variable, is coming from. It's from all these little z-scores. But when we do that, the mean of the random variable will be 0 and the standard deviation will be 1, and that's very important. So our random variable z is called the standard normal distribution, and it's measured in units of the standard deviation. So when we talk about 1 above the mean, that means you're 1 standard deviation above the mean. That's a z-score of 1. A z-score of -2 would mean you're 2 standard deviations below the mean. So this is helpful because we can take any normal distribution and we can standardize it, and then we've got tables that help us measure the percentages in each part of our standard normal distribution table, our graph. Example 6.1, what is the z-score of x when x is 1 and we have this normal distribution? Well, remember, this first number gives us the mean, the second number gives us the standard deviation. So to find the z-score, we're going to take the value they give us, 1, minus the mean, 12, and divide by the standard deviation, which is 3. That gives us negative 11 over 3. And if we divide that out, we're going to get negative 3.67. Most of the time when we do z-scores, we're going to round to 2 decimal places, and that's because when we look at the tables, which I'm going to post here after a bit, but when we look at the tables always have 2 decimal places in them, so that would be our z-score. So what that means is that this particular value, 1, is 3 2/3, 3.67 standard deviations below the mean because it's a negative. So that makes it below the mean. Looking at example 6.2, Jerome averages 16 points in a competitive sports game with a standard deviation of 4 points. So again, when we put that in our notation, there's your mean, his average, and there's his standard deviation of 4. Suppose Jerome scores 10 points in one game. So in other words, x equals 10. And already calculating it for us, the z-score is negative 1.5. We could do that. It would just be the z-score is 10 minus 16 divided by 4. That's negative 6 over 4, which is negative 1.5. But I gave it to us, so it's right there. Interpret this result with respect to the mean and in the context of the competitive sports game. So that means his score was 1.5 standard deviations below his average. And when we look at our normal distribution and the percentages, if it's 1.5 standard deviations below his average, that means he did really poorly compared to what he normally does. He's normally right around 16, but he was 1.5 standard deviations below that. So again, I'll kind of maybe bring this up in a minute. Well, actually, let's do it right now. So our picture, and we're going to see this again. We looked at it earlier in the semester, but we're going to see it again. We know that 68% of the data is in this range right here, which means you've got 34% and 34% here and here. Okay, and here's 2 standard deviations, and this one is, I think, what was it, 12.5, something like that. We'll see it in a minute. It might be 13.5. But anyway, he's about halfway between here. We know that 50% of the data is this way. Then you've got another 34% of the data if we go to here. 34 more. So that means 84% of the data is above this. And then finally, we've got even a little more. So you're probably looking at 90% of the time he does better than what he did in this game. So he did really poorly compared to what he normally does in his game that he's playing. Some properties of the normal curve. The curve has inflection points, those points where the graph changes curvature at 1 standard deviation away from the mean. That means when you draw that, and you can see here in the middle, it's curving down, but then it starts curving up towards the outside. Well, those points right there where it changes, those are inflection points, and that happens at 1 standard deviation away from the mean. The total area under the curve is equal to 1, and that makes sense because it's representing our probability, and we know probability always equals 1. So that's the second characteristic. The third one, the area under the curve to the left of the mean is equal to the area under the curve to the right of the mean, which equals 0.5, and we already saw that in the picture that it was 50% to the left and 50% to the right. So as a decimal, that's 0.5. Number 4, the graph tails off towards the horizontal axis to the left and the right. Now my picture, you can't really tell, but this actually never touches the x-axis. It actually continues going very, very close to the x-axis, but never quite touches it. It just flattens off near the zero line there, but it never actually touches because your probabilities on those are never actually zero. They're just very, very, very small as you move really far to the left and really far to the right. And then finally, number 5, the empirical rule will hold, and that was the rule that we had seen a couple chapters ago, and we're going to revisit that in this section. So here is our empirical rule. It states the percentages of data in a normal distribution within 1, 2, and 3 standard deviations of the mean are approximately 68%, 95%, and 99.7% respectively. So within 1 standard deviation, we've got the 68%. Within 2, we've got 95% of the data, and within 3, almost everything, 99.7%. And we're going to see the pictures of that here in just a minute. So this is a picture we saw earlier in the semester. We can see that we've got in our 1 standard deviation from here to here, we've got that 68% approximately. Within 2 standard deviations of the mean, we have that approximately 95%. And then within 3 standard deviations of the mean, we've got the 99.7% approximately. We can break that down even further, and again, this is in your notes, but it might be a good thing to kind of write down. I was wrong, it's 13.5%, not 12.5. But these things you might want to write down. I know it's in your notes, you might want to circle it to help you kind of remember, but each of these sections, because your middle 68% is right here and it's symmetric, that means each side gets 34%. And then when you have the 95% here, you've got an additional 27% getting split up between these two areas. So you got 13.5 and 13.5, and then you've got your 2.35 beyond that and your 0.15 after that. So each of these sections gets its own specific percentage. And again, these are approximate, but they're pretty close to these values. So that helps us figure some of these things out. I put the table down there, or the graph down there at the bottom to help us with this. We're going to revisit example 224. And we've got our peanut butter jar prices, the standard deviation and the mean. Standard deviation is 0.26 and the mean is 3.68. So here's what that means. The middle number, remember, is the mean. So right here is the 3.68. And that's $3.68. Remember, each of these lines represents a distance of 1 standard deviation. So if we have that mean, 3.68, and we add 1 standard deviation, that's 3.68 plus 0.26. So that I don't mess up, I'm going to grab my calculator here, 3.68 plus 0.26. So this next line is going to be at 3.94. I would put it at the bottom, but I don't have space down there, so I'm just going to put it in the middle. Then if we add 0.26 again to get to 2 standard deviations, we're going to get $4.20. And then if we add the 26 cents again to get to 3 standard deviations above, we're going to have 4.46, $4.46. So that's the standard deviation markings above the mean. To get to the standard deviation values below the mean, we're going to take 3.68 and subtract 0.26. That'll bring us down for this one to be 3.42. If we subtract 0.26 again, that'll bring us down to 3.16. And if we subtract 0.26 again, we're going to get $2.90 here at the 3 standard deviations below the mean. So how does this affect, or how do our prices compare? So $3.99 is going to be in this range right here, just a little bit above 1 standard deviation. $3.79 is going to be in this range right here, probably about in the middle of that. $3.59 is going to be in this range right here, in that first standard deviation below the mean. $3.75 is going to be, again, in that area, pretty close to that other green arrow. And then $3.29 is going to be over here to the left in this region of the graph. So why are we looking at this? Well, if we look at these and we interpret our answers in terms of the in context of the empirical rule here, notice that 3 out of our 5 values, 3/5, are within 1 standard deviation to the right and 1 standard deviation to the left. Well, 3/5 is 60%. According to the empirical rule, we should have 68% in that range. So that's pretty reasonable, isn't it? If 60% of those 5 numbers are in that range, that's pretty close to being what we would expect. Now, if we go 2 standard deviations each direction, notice that gets us all 5 of our values. So that's 5 out of 5, which is 100%. According to the empirical rule, we would expect 95% to be in those ranges. But since our sample is so small, it's not really unreasonable to say that 100% of them are in that range. I mean, 95% is pretty close to 100. So according to our empirical rule, yeah, it seems that this data is probably fairly normally distributed, even though there's only 5 numbers in our population, I guess is what they're giving us, or our sample. So that's pretty reasonable compared to our empirical rule. The 60% compared to the 68 and the 100% compared to the 95, that's pretty reasonable. Can't get much closer than that. So again, for the benefit of me having to do these problems and being able to write them out nicely, we're going to have that graph put at the bottom there. Example 6.4, the Acme company manufactures widgets. The distribution of widget weights is bell-shaped. The widget weights have a mean of 51 ounces and a standard deviation of 4 ounces. Use the empirical rule to answer the following questions. So again, our mean is 51 and our standard deviation is 4. That means the mean goes right here. I think I can fit this one in at the bottom. Right here at the bottom, we're going to have 51, right in the middle. Then when we add a standard deviation, our next marking here is going to be 55, 51 plus 4. When we go another standard deviation, we're going to have 55 plus 4 more is going to be 59. And if we go one more standard deviation, 59 plus 4 is going to be 63. So again, we're just going up 1 standard deviation value each time. When we go down below the mean, 51 minus 4 is going to bring us down to 47. If we subtract 4 again, we're going to get down to 43, and then we'll get down to 39 for that 3 standard deviations below the mean. So now that we've got that marked, our first question is asking, we've got 99.7% of the widget weights lie between what 2 weights on our graph here? Well, we know that 99.7 is 3 standard deviations each way. So 99.7 would mean that we are between the 39 and the 63. So you may just have those as boundaries, or sometimes they will put that in interval notation and they'll say, okay, it's between 39 and 63, and they'll put those in percentages. That means, or not percentages, parentheses. So that means you're looking at everything between 39 and 63. Those are the boundaries for the 99.7%. For part B, we're back to our picture again, and the question is asking what percentage of the widget weights lie between 43 and 63 ounces. So here's our 43, here's our 63, and how could we figure out the percentage of widget weights that lie between those two? Well, there's a couple ways to do this, and I know in class we had a couple when we had the class session last time, we had a couple different ways. I'm going to go with this one. I know from our empirical rule that the distance from here to here is 95%. Then we know that we're going to add this extra little chunk to it, 2.35%. So 95 plus 2.35 is going to give us 97.35%. And that is the percentage of values that would be between 43 and 63 ounces. For part C, it's the same situation. It says what percentage of the widget weights lie above 47%. So this time, here's our boundary, 47%, and we're looking everything in this direction. Well, again, there's probably an easier way and there are some harder ways, but probably the easiest way in this case is to remember that 50% of the values are above that mean. And then we can simply add the 34% more. So if we take that 50% plus 34%, we're going to get 84% of the values are above the mean. Another way to do it, and you could do this, is you could just add 34% plus 34% plus 13.5 plus 2.35 plus 0.15, and you can just add them up, and that would give you the same answer. But if you can think of a little bit of a shorter way, that's probably going to be to your benefit. But that's how we use our table. We know the percentages for each of those sections of the graph, and so we can find the different values based on that. For your homework, you've got 10 graded problems. Again, the earlier you get started on those, the better. Please don't be afraid to reach out and ask for some help if you get stuck on something, and I will try and respond as soon as I can.